Welcome. Today is Casual Friday, November 20th, 2021. Today we're going to talk about how they pump up electrons to the size of a muon electron. That's 207 times the mass of the electron. And the easiest ways to do that is just to take a laser beam, take a high-powered laser beam, and shoot it at a group of electrons. And then those electrons accelerate, and some of them get blown up to the size of muons. And you instantly have a muon heavy electron stream. Okay, you just shoot the laser beam at the electrons and they take off. Okay, now others have a more sophisticated process. Okay, there's a three laser technique. Okay, they use gamma rays. Okay, so they take a high velocity electron beam and they crisscross three lasers, gamma lasers, okay, which is, I don't know how they do gamma rays. Very few people will use high energy lasers. I'm surprised they don't blow up their lab if they're actually using, I wasn't sure if it was a theoretical thing or an actual thing. I mean, the way Chris Rogers talked, it seemed to be, actually Chris Rogers talked about a Large Hadron Collider experiment. Anyway, so it was someone else that talked about the gamma rays hitting an electron beam and changing the electrons to muon electrons at 207 times the mass. So an electron has a rest mass of 511 kiloelectron volts. Now, rest mass is also another way to say inertia. So if a particle has a rest mass, it has inertia, which is resistance to acceleration. Okay, so and we know that light waves have momentum. Okay, the massless photon, the massless photon wave, which is not in dispute. The wave nature of electromagnetic waves is not in dispute. Okay, so since the photon has no rest mass, then the momentum that is carried by an electromagnetic wave must be carried by the medium particles of the wave. So electromagnetic waves propagate in a medium of matter particles that have a rest mass. Now, this rest mass is so tiny that we cannot touch these particles, okay? And I call these particles God particle ones. And I define them as the tiniest particle of mass in the universe. And we know that electromagnetic waves propagate in this medium of God particle ones. And we know that the God particles are under pressure because of the cosmic microwave background radiation. So the CMBR, our universe, produces all sorts of different waves, from X-rays to radio waves to thermal waves, all sorts of different waves. And for those waves to harmonize to one level that is at 2.752 Kelvin or 25 Kelvin to harmonize to that level, they have to bounce back and forth from the edges of the universe. So that means the universe is finite. And we know that the universe from the Hubble flow redshift, which is an excellent barometer for measuring the distance from which the original star or galaxy sent out the electromagnetic waves. So the Hubble flow redshift, the cosmological redshift, is an excellent way to determine how far away the light source was when it emitted the light. Okay, so we know that the universe is at least 22 billion light years across, has a diameter up and down every which way of 22 billion light years. Okay, so for the light waves to bounce back and forth an infinite number of times and redshift till they can't redshift no more and create the cosmic microwave background radiation, they have to bounce back and forth an infinite amount of times. So you take 22 billion years and you multiply it by an infinite number of times, excuse me, and you know that the universe is infinitely old. And you also know that the universe is finite, and you know that the GP1s are compressed because that's the only way waves can compress in a gaseous particle. Just as sound waves can only compress at a high enough atmosphere pressure. So the pressure for a sound wave in order to propagate has to be high enough. If you get too high up in the atmosphere and the air pressure gets too low, then the sound waves can't propagate. The same thing is true even though there's high GP1 ether pressure throughout the universe at the event horizon of a black hole. Okay, what a black hole is, it's more than 2.16 solar masses of neutronium that makes up a neutron star. Once you get above that, then the neutronium creates an event horizon. It absorbs the heat, it absorbs the GP1 so quickly that the pressure between the GP1s that the light waves propagate in gets so light that the waves can't propagate in it anymore. So a massless photon can't be pulled by gravity, okay? But electromagnetic waves can be decompressed enough so that they can compress and decompress and make the wave. So that's what neutronium does. Once you get above 2.16 solar masses of neutronium, it develops an event horizon and the electromagnetic waves cannot propagate anymore. Now, we know this because stellar black holes, let's say 5 solar masses or so, they have very strong tidal pull. So if you fall into the event horizon of a stellar black hole, you will be spaghettified. Your legs are going to separate. And the same thing happens to a star. It gets spaghettified if it develops an accretion disk. Now, a supermassive black hole, on the other hand, the neutronium is near the center and it's a very small part of the event horizon. So the event horizon is just the area where the GP1 ether pressure is too low for electromagnetic waves to propagate, okay? The way to understand this, a massless photon can't be pulled into a black hole. But the tiniest particle in the universe that's under pressure can be pulled into a black hole. Essentially, the black hole is below absolute zero and it's sapping heat from the universe and it's sapping it so fast that it decompresses the GP1s and light waves cannot propagate within the event horizon of a black hole. Okay, so we sort of went off tangent here because what we're going to discuss is how an electron gets pumped up by 207 times to a muon electron that has the same properties but is 207 times, has 207 times the rest mass. Okay, but the rest mass is not quite applicable here because it'll instantly, in a millionth of a second or 2 millionth of a second, it will decay back to an electron. It'll emit the energy as gamma waves. Now, the reason it does this, now what the lasers do, whether in the stream of electrons or straight onto a bunch of electrons, what the laser beam does and what the laser beam is, it's highly compressed God particle ones and decompressed, okay? And if it's light frequency, then they're harmonized to a light frequency. So you have a very high amplitude light source, okay? So the electrons are highly compressed and then they're highly decompressed. The net effect of the laser, of the high compression of the laser, is that GP1s keep getting pumped into the electron sac until it gets blown up, okay? So you still have this indestructible electron sac that at rest has 511 kilovolts of electricity, and you blow it up 207 times, and then it has like 105 MeV, okay? So that's a million electron volts. So from 511, you go to 105 MeV in the same sac, okay? Now, as this electron sac expands, okay, now it's pulsate and it's permeable at 511 keV, but at 105 MeV, the holes get bigger, okay? So once it gets out of the range of the laser beam, okay, then the God particle ones pop out real quick. I mean, the pressure, it's a 105 MeV compressed GP1s inside. Now that is the stored energy of a proton sac, of an electron sac, of a neutron sac. The energy inside of it is stored as compressed GP1s. But if you take a tiny electron sac and you blow it up to a muon sac, then the holes get bigger. It gets stretched and the holes get bigger, and the pressure may be 1,000,000 times higher or 1,000 times higher, because the laser beam compresses the GP1s and decompresses, and they're high amplitude compressions. So these high amplitude compressions pump these God particle ones inside. They expand the holes, and then the holes are bigger and the pressure is higher, and out come the GP1 as gamma waves. And then they measure the gamma waves and they say that particle had 105 MeV of energy. Okay, so that's how you store permanently and temporarily, okay? So there are only 4 particles that can permanently store both mass and energy, okay? And when a particle gets bigger and has more mass, it also has more God particles inside. And it also has more energy because more God particles are compressed inside an indestructible sac that was minted inside the center of neutron stars. So like diamonds are minted inside the Earth, these nucleon sacs, okay, these nucleon sacs are minted in the neutronium inside black holes. They're minted inside the neutronium of neutron stars. They're minted inside white dwarfs. Okay, and they're embryonic. The way to think of the neutrons in a neutron star or in a black hole is as embryonic neutrons. So how we get more hydrogen is the neutronium warms up from the cosmic microwave radiation. After it stops accreting over infinite time, the neutronium in a neutron star or in a black hole, it warms up. It warms up from the cosmic microwave background radiation. It absorbs this heat, and once it gets back up to absolute zero, okay, now you say you can't have temperatures below absolute zero. Now, the way physicists determine, there are two ways to determine temperature. One way is entropy. Entropy has to do with disorder. So what they say in thermodynamics is the higher the entropy, the hotter the temperature. Okay? And the denser the object, the lower the entropy, the lower the temperature. Okay? Now, in order to get a neutron star, which is 100 trillion times Earth density, okay? So, neutronium, if you take 100 trillion Earths and you put them in the volume of the Earth, you would have a neutronium ball of about 300 million solar masses. It's 300,000,000 solar masses can be put into the size of Earth, into the volume of Earth, and that will result with an event horizon. Okay, and if you have 300 million, the ratio is 5.8 per solar mass. So if you multiply 300 million solar masses by 5.8, you get about 1.6 billion kilometers diameter of the black hole. So the neutronium is all going to fit in the volume of Earth. But the black hole is going to have a diameter of over 1 billion kilometers. Okay? That's a lot to take. Okay? I'm really throwing this stuff fast at you. If you check my old videos, it'll be clear to you. Okay? So, anyway, we didn't continue. Okay, so we need to continue with this muon and the storage of energy. So both mass and energy are stored inside 4 sacs. And the neutron sac, the proton sac, the electron sac, and the neutrino sac. Okay, those 4 sacs can permanently store both mass and energy. The mass that they store is God particle 1s. The energy is stored, the potential energy inside a matter particle is stored in the form of compressed GP1s. The GP1s are compressed, and we know this because when a proton rendezvous with an antiproton, they're both spinning, and they make contact and they rip their sacs apart. Once they rip their sacs apart, the potential energy stored inside their sacs, the God particle 1s, come out as gamma rays, and they go off in different directions, okay? So that's how matter and antimatter annihilates each other. Now, physicists have a problem because they think that energy pulls a proton and an antiproton out of vacuum at the same time. Well, first off, that's impossible because physicists know they would annihilate each other. So they're trying to make an excuse for their logic, okay? What actually happens is embryonic neutrons are what constitutes a neutron star. And when they get pumped up with enough GP1s to get up to absolute zero, okay, let's say a neutron star has 2 solar masses. Well, when you pump in those God particle 1s and it warms up to absolute zero, 2 solar masses might be 36 solar masses. Okay, we don't know the exact ratio. All we know is that the neutrons in a neutron star are embryonic neutrons, and that they're at 300 trillion Adoni degrees below absolute zero. Adoni Kelvin degrees below absolute zero. Now we know this because the entropy of a neutron star has to be much, much lower than the entropy of our stuff on Earth, okay? Now, you say our stuff is warmer, okay? But okay, so you get to absolute zero and you still have matter, okay? Like, let's say hydrogen clouds are at 10 degrees Kelvin, okay? That's not far from absolute zero. And the cosmic microwave background is at 2.72, okay? Now, matter is going to have a certain entropy, okay? But the electromagnetic waves, but once you get to 100 trillion times Earth density, the entropy has to be much, much lower. So that means that a neutron star is very, very cold. And what I do to calculate the temperature is I take the multiple of Earth density, okay? So a neutron, the neutronium in a neutron star is 100 trillion times the density of Earth. So I multiply that by 3, and I say the temperature of the neutronium inside a neutron star is 300 trillion times below absolute zero. 300 trillion times Adoni Kelvin degrees below absolute zero. And that once you warm up that neutronium, once you bring it up to absolute zero, for let's say you got 2 solar masses, you're going to end up with 36, or you're going to end up with 80, You're going to end up with a lot more hydrogen, because once you pump up that neutronium to a neutron at zero or absolute zero, it's going to decay into a hydrogen atom. So that's how the universe is continually getting our infinitely old universe in a finite volume. That's how it keeps renewing itself. It's going to go on forever. Don't believe these people. Our universe has no beginning and it has no end. It's going forever. I'll leave you with that. I'm losing my voice. Happy Friday, Casual Friday, November 20th, 2021. Bye.